We have been solving linear systems that consist of two equations and two variables. The graph of a linear equation in two variables is a straight line, and the solution to a system of linear equations in two variables is the intersection point of the two lines. However, linear systems can also contain three equations in three variables. The graph of a linear equation in three variables is a plane. To solve the system of three equations and three variables means to find the intersection point of all three planes, expressed as not an ordered pair this time, but an ordered triple, x, y, z. So just as we saw with linear systems in two variables, different orientations are possible for linear systems in three variables. One possibility is that all three planes intersect in a single point, almost like the corner of two walls and a ceiling meeting in one spot. And in this case, we have a consistent system with one solution. That solution is described by an ordered triple xyz. Consistent systems can also have infinitely many solutions. So, for example, the three planes can intersect, but not necessarily in a single point, but in a line. Because there's an infinite number of points along that line, we would say that system has an infinite number of solutions. Like we saw with linear systems in two variables, it's also possible that all three equations describe the same plane. And in that case, every point on the plane would be a solution to the system. So consistent systems can also have an infinite number of solutions. Inconsistent systems with no solution can happen in a couple of ways as well. You may have the possibility that all three of your planes do intersect, but all three planes don't share a point in common. Or all three planes are parallel. For our purposes, we'll be working with consistent systems with one solution. Now, three variable linear systems and even larger can be solved by substitution or elimination, but the process becomes more tedious to manage, as you can imagine. For larger systems, we can use matrices and a graphing calculator to solve the systems very efficiently. And I think you'll like this method in the end, but it takes a little bit of background work to get there. So we need to talk about what a matrix is and how we're going to apply it to solving a system. And we're specifically going to be using something called an augmented matrix. Remember, matrix is singular, matrices is plural. So what is an augmented matrix? First of all, a matrix is a rectangular array, which is a fancy way of saying a table of numbers. An M by N matrix has M rows. So remember, rows are horizontal. So if I count the rows here, I have 1, 2, and then I keep counting until I get M rows. And N columns. And remember, columns are vertical. So if I count the columns here, I have 1, 2, 3, 4, 5, and then it's going to stop with some number N. So each individual entry that belongs to a specific row in a column is expressed as A sub ij. So for example, A sub 1, 1 is the entry in row 1, column 1. Or if I look at the entry A sub 1, 2, the subscript means that it belongs to the first row and the second column. So if I go down to the next row, I have the entry in the second row and the first column. Now, if I look at the general entry, A sub 1j, this just means it belongs to row 1, column j. J just represents some intermediate value between 1 and n. So let's see if we can fill in the blanks where the entries are missing. So again, this is row 2, this is column 2, so we could call this entry A sub 2, 2. Moving on to the next blank, we're still in row 2, so my first subscript would be 2, but the column here is called j. And then finally, A sub 2, and then n, whatever our last column happens to be. If we go down to the last row, that's going to be the mth row. The next entry is still in row M, so its first subscript would be N. The second subscript describes the column it belongs to, so that would be A sub M2. This one would be row M, column J, and then our last entry, row M, column n. Now remember, this is an m by n matrix. It has m rows and n columns. That's called the size or perhaps the dimension of the matrix. Now, we can take a system of linear equations and represent it by what we call an augmented matrix. Augmented means enhanced. So we're going to take a square matrix and enhance it with an additional column. So here's what it looks like. What we're looking at is a system of 3 equations in 3 variables. So x plus 3y plus 2z equals 1. Remember, each one of those equations describes a plane. So when we solve the system, we're looking for the intersection of those planes. What we're going to do is simplify that system and just work with the coefficients and constants of the system. So if you look at equation 1, x plus 3y plus 2z equals 1, I'm going to enter that as row 1 in my augmented matrix. So in column 1, we're going to pick up coefficients of x. In column 2, coefficients of y. In column 3, coefficients of z. And when we write this by hand, this will be a solid line. That represents the equals in the system. And on the right side, we're going to have the constants of the system. So in equation 1, we have coefficients 1, 3, and 2. So you can see those are our entries 1, 3, and 2. And on the right side of the equals, we have the constant 1. So we have a 1 on this side. Looking at equation 2, we have coefficients 2 times x, 1 times y, negative 1 times z, and that equals constant 2. And for our third equation, we have coefficients 1x, 1y, 1z, and that equals 2. So this left side is what we call the coefficient matrix, because it contains all of the coefficients of the system. And this last column is what we call the augment. And that contains the constants on the other side of the equals. So when we solve a system using this matrix method, that's going to be our first step. We're going to take the system out of its ordinary notation and rewrite it as an augmented matrix. Then we're going to do operations within that matrix to solve the system, or at least our calculator will. That method is called Gauss-Jordan elimination. Gauss-Jordan elimination is a numerical process that uses elementary row operations to transform an augmented matrix into reduced row echelon form, also called RREF by our calculator, with ones along the diagonal and zeros above and below the ones. Okay, that was a lot of information. So when we solved a 2-variable system by elimination, we were multiplying the equations by something, we were adding the equations together. That is what is going to translate into elementary row operations. So all of the same processes that we use to solve by elimination, our calculator at least is going to do those same operations within the matrix, within the table. And the goal is to take our system or our matrix from its original form and transfer it into what's called reduced row echelon form. Remember RREF, that's the command from the calculator. So what is this reduced row echelon form? Well, here we have a 2 by 3 augmented matrix. That's 2 rows and 3 columns. Notice we have ones along the diagonal and zeros above and below the ones. Also, here is a 3 by 4 augmented matrix. And again, it's in the same pattern with ones along the diagonal and zeros above and below the ones. Now, this is a desirable form because I can simply read the solution to the system out of the augment. So to show you how this works, let's look at our 2 by 3 matrix here, and let's translate this back into algebra. Remember, column 1 contains coefficients of x, column 2 contains coefficients of y, the vertical bar is the equals, and we have constants on this side. So if I translate that back into an equation, that would be 1x plus 0y equals some number a. And if I simplify that, that means x equals a, right? And equation 2 we could write as 0x plus 1y equals b, and we could simplify that into y equals b. So if I look at x equals A, y equals B, that's the ordered pair solution to the system. So once we get the matrix into this reduced row echelon form, then the solution to the system lives right there in the augment. So if I'm looking at a larger system, then the ordered triple solution is also going to be located in the augment. It would be A, B, C. So once a matrix has been transformed to reduced row echelon form, the solution to the system will appear in the rightmost column, which we also know as the augment. So again, the first step is to get our system out of algebraic form into the form of an augmented matrix. Then we're going to enter that information into our calculator. The calculator is going to apply the elementary row operations to get it into this RREF form, and then we'll be able to read the solution in the augment. So the steps that you see here on your notes are how to apply that process with your calculator. So we're going to go through this process on the examples, but remember that's written in your notes if you need to go back and refer to the process. So let's try to solve these two systems using the Gauss-Jordan elimination method, which is code for the calculator and the RREF form. And we're not doing this by hand. And then we'll express the solution as an ordered pair or triple. So on example A, we have two equations and two variables. So we're looking for the intersection point of two lines as an ordered pair. In order to use this matrix method, the original equations must be in general form. So on equation 1, I need to subtract 3y from both sides. This looks like 2x minus 3y equals 2. And equation 2 is already in general form, so we can leave it as it is, 6x plus 6y equals 1. So that's our system in general form. What we want to do is rewrite this as an augmented matrix. So we're going to have one row for each equation and one column for each variable and the constants. So we're going to need a 2 by 3 augmented matrix. In row 1, we're going to pick up the coefficients of the system. So x comes first. Remember, in column 1, we have coefficients of x, column 2, coefficients of y. The vertical bar represents equals, and we're going to put the constants on the right side. So in row 1, column 1, we're going to pick up the coefficient of x, which is 2. Next, we have -3, and then in the augment, we'll have a 2. For row 2, we'll pick up the coefficients of equation 2. So we have 6x plus 6y equals 1. So that is our augmented matrix, which represents the original system. Next, we want to enter that information into our calculator and tell the calculator to transform this into reduced row echelon form. So if you notice on your calculator on the left side of your keypad where you see the x to the -1 button, above that x to the -1 you can see matrix in blue. So the first thing I'm going to do is go to that matrix menu by typing second and then matrix. And I want to highlight the second item in the menu at the top. I want to use my right arrow key to highlight math. I'm going to tell my calculator to do some math to this matrix. Now be careful here. I'm going to go way down to the bottom of the list with my down arrow key until I see RREF. Notice there's an REF, that's row echelon form. We don't want that one, it's not unique. We want RREF, reduced row echelon form. So make sure you pick up the double REF. Once that's highlighted, you can press enter, and that's going to take me back to my home screen. So I'm telling the calculator to transform the matrix into that reduced row echelon form. So the next thing I need to do is enter the matrix. And we're going to do that from the F3 menu. So if you look at your zoom button there on the top row, in green you see F3. So to access that F3 menu, I'm going to use my green alpha key and then type zoom. And this opens up a matrix menu. So the first thing I want to tell my calculator is how big do I want this matrix? So I'm going to use my arrow keys to highlight 2 rows and 3 columns and press enter to make those changes. And once you have your rows and columns set, you can highlight OK and then press enter. And it's going to adjust an appropriately sized matrix. And here's where I can enter my information. So the first entry we have is 2. I'm going to use my right arrow key to type in the next entry, which is -3. And then the right arrow key, now the vertical bar is not shown on the calculator, but we know we're now located in the augment, so I'm going to hit the 2. And then my right arrow key again, and finish out this row, plugging in our entries. And then I'm going to use my right arrow key to get out of that matrix and close parentheses. So I'm telling my calculator, take this matrix and put it in that reduced row echelon form. So let's press enter. So this one, it looks like it gives us decimal values. We don't want the decimals, we want it to be in fraction form. So let's press our math button over here on the left and choose number 1 fraction, and it'll clean that matrix up a little bit for us. So that is our reduced row echelon form. So we're going to record that information on our work. So row 1, we have 1, 0, and 1/2. I'm going to go ahead and enter that vertical bar to separate out the augment. And row 2, we have 0, 1, and -1/3. So the beauty of this method is the solution to my system is right here. So my ordered pair XY solution is 1/2 -1/3. To build some confidence in this method, let's make sure that it's correct. So I'm going to look at the first original equation, 2x equals 2 plus 3y, and I'm going to plug in our proposed solution. That is x equals 1/2 and y equals -1/3. Let's see if we have a balanced equation. So on the left side we have a 1. On the right side we have 2 minus 1 or 1. So I'm not going to take the time in this video to substitute it into the second equation, but it would certainly work. And we've got our correct solution here. This means that the 2 lines described by our 2 original equations would intersect in the ordered pair 1/2 -1/3. So at this point we could solve that system by substitution, we could solve it by elimination, or now we have this third calculator method, Gauss-Jordan elimination, that we can also solve the system. As you can tell, once you get to know what a matrix is, that's a pretty efficient and easy way to solve the system. Now let's take a look at this next example. Notice in this example we have 3 equations and 3 variables. So each one of those equations represents a plane, and I'm trying to find the ordered triple location where those 3 planes intersect. So it sounds like a hard problem, but as you'll see with our matrix method, this is a pretty simple problem to solve. So each one of our equations is in general form. Now for 3 variables, that looks like ax plus by plus cz equals some constant d. So everything's lined up and ready to go. So we're going to need 3 rows and 4 columns for our augmented matrix. In row 1, we're going to pick up the coefficients of equation 1. 2, 3, 4, and in the augment we have -2. In row 2, we'll pick up coefficients of equation 2. -1, -1, 8, and 6. And then in row 3, we'll pick up coefficients of equation 3. That's 3, -5, -4, and -8. So that's the information that we want to plug into our calculator. We're going to tell our calculator to reduce that matrix. So it is a larger matrix, but the process is the same. So let's first call up that RREF command from our calculator. Remember, we do that by typing second matrix. We highlight math. And if you're in a real hurry, remember RREF was way down the list. If you want to get there a split second faster, you can use your up arrow key and come up from the bottom of the list and choose RREF. Okay, so once it's highlighted, press enter. Then we want to enter our matrix. So remember, we do that by typing alpha F3. Our matrix has 3 rows and 4 columns. So I'm going to highlight 3 and press enter, and then highlight 4 and press enter. And once I'm happy with that, I will tell the calculator OK. So it gives us a 3x4 matrix. So we'll take our time and plug in our entries. Be careful here. Watch your signs. If we're going to mess it up, it's going to be right here, leaving behind a sign or something like that, typing in the wrong entry. And it always is beneficial to just take a minute, look back over, make sure you have all of your entries plugged in correctly, and then press enter. So we end up with our matrix in reduced row echelon form. I see that decimal there in the very last position, so don't forget you can type your math menu, option number 1, and have it converted into fractions for you. So now we have a 3x4 augmented matrix. So I'm going to record that as part of the solution. So we end up with, this by the way is called an identity matrix on the left. And then on the right, we had entries -2, 0, and 1/2. And as you know, our solution comes from the augment. So the ordered triple solution, x, y, z, then is equal to -2, 0, and 1/2. So if I take that ordered triple and I plug it into all 3 equations, it's going to balance all 3 equations. Graphically, this means that those 3 planes would intersect in this location in 3-dimensional space. So this is a pretty easy method to apply, but you will have to take some time to learn those steps on your calculator.